Hello, in this video I'll be going through some practice problems involving Hardy-Weinberg equations, not to be confused with the Hardy-Weinberg principle, which states that allele frequencies and genotype frequencies will remain unchanged from generation to generation provided that certain conditions are met, which I'll explore in a later video. Now in this one I'm going to explain some practice problems. Now you can see I've written down the meanings of p squared plus 2pq and q squared. Now the homozygous dominant individuals we can represent with 2 capital letters. The heterozygous individuals we can represent as a small a, and homozygous recessive is 2 small letters. And here is the second equation, which tells us the frequencies of alleles, and this one tells us the frequencies of different individuals, different genotypes. Okay, problem 1, we are given that the homozygous recessive phenotype is 36%. Now, we can actually work out an awful lot of information given just 36%. Now, first thing you want to do is you want to convert this into a decimal. Calculate the following: the frequency of the homozygous dominant phenotype. Now, what I want you to do is, before we start looking at the question, we want to work out what we already have. So homozygous recessive, is AA. And I've given that the expression of q squared, and that is equal to 0.36. Now that can easily lead us on to q being the square root of q squared is equal to 0.6. Now that's very good because now we are told the frequency of the recessive allele. That's brilliant. We can also work out p, which is 1 minus q, which is 1 minus 0.6, which is 0.4. Now we have the frequency of the dominant allele. And then from there we can work out p squared, which is 0.4 squared, which is 0.16. That is the percentage of homozygous dominant individuals. And finally we can work out 2pq, which is 2 times 0.4 times 0.6, which I think is 0.48. Yes, okay. Now, what we can do is we can look at the question again and we can say, well, homozygous dominant phenotype, that is the same as 2a's, basically, p squared. Now, one thing I want to state is that it doesn't actually matter if you say p is the recessive allele and q is the dominant allele. These two things are mathematically equivalent, so you're fine either way. Question B. The frequency of the recessive allele. Now remember, the frequencies are just the letters by themselves, and in this case I've given q the identity of the recessive allele. So q, we've already worked out, is 0.6. Now dominant, well I said that was p, and we worked out p to be 0.4. And how about the heterozygous dominant genotype? Remember, genotypes are the products, so, and the heterozygous dominant is this one, 2pq, which we've already worked out to be 0.48. So what I wanted to show you here is that one piece of information, for example, the q squared or the q or p, basically allows you to work out everything else, but it's very important to work out what you have to begin with, so I want to make it very clear that right now I found out q squared. Okay, next one is slightly harder, but following the same principles as the last one, we can approach this the same way. So this tells us that there is a condition that is due to a dominant allele. 300 people were sampled, 180 had the condition. Now we are going to estimate the number of carriers. First thing I want to do is note that if I were to take the number of people who had the condition, that's actually not very useful, because they could be either dominant, homozygous dominant, or heterozygous. That's all these 180 people. What we want to do is we want to focus on the people who don't have the condition, because we know that they have 2 of the small recessive alleles. So we know that 120 out of 300 is basically the number of people who do not have the condition, right? So q squared is equal to 120 divided by 300. Seem to have misplaced my calculator. Hold on. Okay. 100 and, which gives you 0.4. You don't need to be using a calculator for this. And q is root 10 over 5. now that we've worked out all of this, we can also work out p, because remember, p plus q equals 1, so p is 1 minus root 10 over 5. And the last thing we want to do is work out 2pq, which is 2 times p times q. I'm just doing this so I've written out my working. Okay, so that's 2 times 1 minus, you could do 1 minus answer, times the answer, which is 0.4649 dot 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 dot. What I want to do is I want to emphasize that this is not, this is simply a percentage, okay? So this is the percentage out of however many people we were sampling that have the heterozygous genotype, and carriers, I wanted to state, have the heterozygous genotype. So finally, our last step to work out how many people would be to times this by the number of people, which is 300. So timesing this by 300 gives you 139.47. Okay, now I could either round this up or down. That's entirely dependent on like the requirements of the question, but I'm going to say basically 139 people are carriers, and we're done. I hope this video explains something. If you have any questions, let me know in the comments. Thank you.